Good day, dear colleagues. Do you see my screen well? Sorry, do you see my screen well, or?
Yes, we can see well.
Okay, so I'll start. Dear colleagues, I'm pleased to introduce our collaborative research presentation of the topic Edge-based sensor network for critical object monitoring, reliability models, considering the location of failed sensor. This work is a collaboration of effort me, Станислав Скоробогатько, German Fisenko, Vyacheslav Harchenko, and Sergey Yakovlev. Now you can see our agenda. Today we'll discuss motivation, state of the art, and aim of the work, and objectives and introduction section. After that, we will move forward to main results of the research and conclude our results. Motivation. Sensors network hold pivotal significance across a broad spectrum of applications, such as in industrial monitoring to defense-related utilities. And despite the integral role, one key factor that influences the reliability of these sensor networks is specifically the location of some malfunction sensors. Has remained substantially unexplored. The malfunction of sensor can have noticeable implication, severely affecting the network functionality. This invariably leads to the generation of imprecise data and potential causes system breakdowns. Consequently, this is a pressing need to champion the design and implementation of robust and reliable edge-based sensors networks, which can enhance their use in multitude of critical applications. As we enter into the current landscape of relevant papers and scholarship, we find a variety of approaches that have focused on the construction of different Markov models. These methodologies are aimed to boost the particular features within such systems. Despite these commendable efforts, one finds an evident gap in the existing body of these folks. The realm of inquiry into how the placement of sensors within a network impacts system dependency appears decidedly uncharted. It is the precise gaps that our research seeks to address and elucidate future in the course of this presentation. The aim of work. Our purpose is undertaking this study is to devise a proposed theoretical model that measures the ability of an edge-based sensor network deployed for critical object monitoring. We have considered different configuration to this resource, embracing scenario both with and without duplicated sensors in the network. Furthermore, our model also takes into account systems inclusive of failed location aspect, as well as this where the aspect is not integral. Our intention is to provide a comprehensive model that navigates varying sensor network configuration and conditions. Our research endeavors and encapsulate within the following objectives. Firstly, we aim to design a network architecture that is empowered by edge computing capabilities and enhance the functionality of UAVs within sensor networks. Secondly, another crucial object is to create and critically examine a Markov chain-based model specific to sensor networks within these edge-enabled systems. The mathematical model will provide precise assessment of system state, and transitions contributing to the overall system's efficiency, performance, and availability predictions. Lastly, we intend to devise a comprehensive methodology that allows us to quantitatively analyze the availability and reliability of the edge-enabled system that employs our UAVs. Taking together these objectives guide of our research, propelling us towards innovate some solution for developing more reliable and efficient edge-enabled sensor networks. Now on the slide, you can see one of our diagrams. Consider the diagrams which encapsulate a Markov graph representing in sensor network composed of 9 sensors and broken down into a intricate interplay of 55 states. Interestingly, it's observed the functionality persists only in states where there are fewer than 3. It indicates where there's fewer than 3 incidents of double failures within a single area. This is a complex and nuanced scenario that demands a meticulous examination when some conducting analysis and assessment of the overall system availability. Our discussion today will take into account the complexities as we delve further in our study. Kindly note that the graph in question embodies 3 distinctive type of states. The initial states represent an instant with a single sensors in the state of failure. Moving forward, we can see the second state is an indicator of scenario with 2 sensors that have some unfortunate malfunctions. And lastly, the third kind correspondent with the situation where the 3 sensors have some succumbed to failure. The state housing 3 failed sensors invariably results in a system failure. In a related note, within the overall 36 states harboring 2 dysfunctional sensors, 12 of these contributed to a system-wide failure. This is something we need to consider as move forward in our exploration of sensor network reliability. Referring to previous slide on figure 2, we discover that graphical representation can be deslided into a more concise form for an easy understanding and interpretation. In this simplified version, we can see 5 states. The first states embody the state of system functionality at full capabilities and capacities. The second state corresponds to the situation of a single failure within a system. The state number 3 indicates the considering precision of 2 failures. State number 4 represents circumstances where 2 adjacent failures have regrettable lead to the system breakdown. And finally, state 5 symbolizes a total system failure due to some simulation recurrency. This schematic simplification aids in the efficient study and analysis of the impact of sensors failure on our system's operation. Now let's move to our case studies. Description of model. Our discussions now power towards the numerical representation of system reliability. This is governed by a mathematical matrix with the dimensionality of n equals 3. N means quantity of sensors, reflecting the vital fact that 3 simulations fail trigger a system failure. Let us envisage a sensor network consisting of 9 sensors. We tactfully represent its reliability through a 3x3 matrix structure. Within this network, the second level of our computational model houses 36 states, each corresponding to a unique combination of failing sensors. However, these combinations do not cause a total system failure. Upon some unfortunate events, the system reach a state of failure. We find 12 distinctly identifiable states, each representing a unique scenario under which the system has malfunctioned. Within all these third-level states, the system is rendered non-functional due to the concurrent failure of 3 or more sensors. Exploring this numerical representation, we aim to better comprehend the varying levels of system functionality and failure dynamics. Having examined the various possible scenarios of sensors failures, we have thoughtfully formulated an equation. This mathematical approach will strategically calculate the probability of system availability and failure under the circumstances, providing some valuable insights into the potential flaws inherent to the network. This is a vital step toward enhancing system resilience. Upon carrying out of formulated calculation on the system configuration discussed in previous slides, we have arrived at a significant result. The computer probability of system availability is defined as 0.9416. This matrix derived from our strategical probabilistic model unveils crucial information regarding the robustness and readiness of our existing sensor network to withstand potential failures. Result of our analysis. As we can see on this slide, we can move our attention towards the graphical representation that illustrates the correlation between the availability probability and the alternation in the failure rate of sensor expressed as the lambda. This probability change over time and clearly demonstrates the dynamic nature of our system. Upon examining the presented graph, we observe an intriguing pattern unfold. We note that incremental passage of time the system availability represents hereby the probability witnesses a margin decline. This subtly yet crucial trend underscores the dynamic relationship between time and the functioning of the system, hitting in potential areas warranting future investigation and optimization. And let's shift to another significant graphical representation. This graph liquidates the relationships in between availability probability and change number of sensors denoted by N and P, representing availability. An observation surface from this visual data representation as the number of sensors in the system in the system increases, the probability of the system's availability shows a notable decline. This downward trend underscores the critical balance between sensors quantity and system availability, suggesting potential challenges and some considerations in system design and maintenance. And let's move to our conclusions. To conclude our work, our proposed model sets some groundwork for smooth and dependable network operations, even in the face of some inventable disruptions, such as alternations in network topology or some node failures. A range of availability metrics, including some reliability or availability of our system, are examined in our analysis, enabling us to make some informed assessment about network performance. This ensures that our model is not only theoretical, but is capable of practical delivering results. The cognitive tool we have presented today has been scrutinized under two separate scenarios. Firstly, within a context where the application is permitted, and the scenario without it. And I think with our future point of progress will be exploring of models adaptability and deployment in new environments. And dear colleagues, thank you for your attention. With this, I end my presentation and waiting for your questions.
Thank you. Thank you. Dear colleagues, have you a question? Mr. Stanislav. Dear colleagues, have a question. I have some question. We have the result your report on slide 20 and 30, maybe. How you take this result? How you take some characteristics which presented by your updating?
Okay, yeah, I understand. Mainly it's technical characteristics of the sensors. And the first thing is, for example, some fire sensors, smoke sensors, and stuff like that. And the second one, it's results from existing works from state-of-the-art section. We take into account these results and evaluate it in our work. And I think that is most of our source data for the modulation of our results.
Thank you very much. Dear colleagues, have a question? Thank you very much, Mr. Stanislav.